All right, good morning, everyone. So lecture 15, 124-105, where we will look at some examples of applications for electromagnetic induction. So yesterday we learned about electromagnetic induction. We saw that if you have a magnetic flux that changes through a loop, that generates an induced voltage or EMF. So when we say EMF, that's the same as the voltage. And mathematically, we describe that using Faraday's law. So Faraday's law is this equation here, which says that if the flux phi sub B changes with time, then voltage is generated. And flux, we define that as the magnetic field times the area times the cosine of the angle between the magnetic field and a vector that is normal or perpendicular to the surface whose area is A. All right, so in other words, we can generate a voltage if we change any of these variables here. If we change the magnetic field magnitude, the area of the loop, or the orientation between the loop and the magnetic field. And of course, because this is a rate of change, we can also create a voltage by changing how fast any of these variables changes, right? And then, of course, if you have more than one loop, say you have n loops, each of those loops will generate a voltage because the magnetic flux will change through each of those loops. And therefore, the total voltage that's generated is just the number of loops times the rate of change in the flux. All right, so one example of electromagnetic induction is the electric generator. So here you have a magnetic field, say you have North Pole and the South Pole of a magnet. Of course, we know the magnetic field goes from the North Pole to the South Pole, right? So there is magnetic fields in this region between the poles. If you put a coil of wire between that region and you rotate that wire right through that region, notice here in the diagram, you are changing the angle between the magnetic field and the normal vector to that wire. What happens then is you are essentially changing the number of magnetic field lines that's crossing the loop, right? So here in this first instance where the angle between the magnetic field of course goes from North Pole to South Pole, and the normal is the vector that's perpendicular to your surface. So in this first case here, the angle between the magnetic field and the normal vector is 0 degrees. You have maximum number of field lines crossing your surface. Okay, but then if you rotate your coil, notice how the angle changes, and therefore the number of field lines crossing your surface also changes. In this instance here, where you have the magnetic field line being perpendicular to the normal to the surface, hence the angle is 90 degrees, you almost have zero, well, you have zero magnetic field lines that are crossing your surface here. So you're going from maximum field lines to minimum field lines, and if you continue your rotation, you will go back again to maximum field lines crossing the surface, right? So in essence, by rotating the coil in the magnetic field, you are changing the magnetic flux or the number of magnetic field lines crossing your loop. And if we can then do some, we can then describe the rotation of the loop in terms of its angular velocity omega. Okay, the angular velocity, if you recall, is equal to the angular displacement theta with respect to time, right? So this one here is the angular velocity. So therefore, well, you can rearrange this and get an expression for the angle theta that's equal to omega times t, angular velocity times time. And if you substitute that to your magnetic flux equation, you then have BA cosine omega t. Okay, note there that omega can be defined as 2 pi times the frequency. So frequency is the frequency of rotation. So how many rotations you make, the coil makes per second in this magnetic field region, that's the frequency there. Okay. So we have then rewritten the equation for the magnetic flux using the angular velocity, or how fast the coil rotates in the magnetic field region. So if we look at Faraday's law, because we are changing the magnetic flux through the loop by changing the angle theta, Faraday's law tells us that a voltage is generated in the loop according to this equation here, where flux is now BA cosine omega t, right? Written in terms of the angular velocity. Right. We can take the derivative of this equation. ABA is of course constant, so we can rewrite this equation as negative n times b times a, and taking the derivative with respect to time of cosine omega t. Okay. Right, we can evaluate the derivative of cosine omega t. The derivative of that is negative omega sine omega t, because the derivative of cosine is negative sine, and then you take the derivative of the argument omega t, which is omega. In other words, we can write the voltage that's generated when you rotate the coil in the magnetic field to be equal to n times b times a times omega sine omega t. Okay, so what this tells us is that the voltage that's generated is now a sinusoidal function, sine function. So if we look at the voltage that's generated, you then have this time varying voltage according to this sine function with respect to time. As the coil rotates in the magnetic field region, you start with, say, a minimum voltage that's created going to maximum, minimum, maximum, and so on. So we call this sinusoidally varying voltage that's generated in the coil to be alternating voltage or AC voltage. Right, and then of course, if you have a resistor in your loop, then you will then induce an alternating current, or this is what we call AC. Sometimes it's called AC current, but AC stands for alternating current. Alternating because the coil alternates from maximum flux to minimum flux, and then as it rotates in the magnetic field region. In essence, also the magnitude or the amplitude of the voltage and the current is alternating between positive and negative values. So we can see here that AC voltage and AC current, they are a consequence of electromagnetic induction. You have a changing magnetic flux through the coil, which generates an alternating voltage according to Faraday's law, which therefore generates an alternating current. Right? Good. So by starting our discussion from what a magnetic field is, and going into magnetic fields produce currents produce magnetic fields, and changing magnetic fields produce currents, we are now able to define what an alternating current is. And in our next lectures, we will then analyze AC circuits which contains alternating currents. But for today, let's look at another example of an application for electromagnetic induction. So we've seen that the generation of alternating currents using an electric generator is a consequence of electromagnetic induction. Well, the transformer is also an application of the electromagnetic induction. A transformer, maybe we're familiar with it. It's a device that increases or decreases the voltage, the alternating voltage via electromagnetic induction. Okay. So yeah. So let's discuss how a transformer works and where does electromagnetic induction come in the understanding of a transformer. So in a transformer, you have this core. Okay? This core usually is made up of iron, because we've seen from the last lecture that iron increases the magnetic field because it's ferromagnetic. Okay, usually the iron is laminated to reduce losses of energy. Okay, so you have this core, and then on one side of the core, you have wire that's coiled around that side. We call that the primary coil. And then on the other side of the core, you have another set of wire that's coiled around. We call that the secondary coil. Okay. Right. So what happens in the transformer is that if you connect the primary coil to an alternating current source or an AC source, right, then of course current will flow through this wire. Okay. Right, so you have current flowing through this wire. This is a wire loop, and we learned that currents will create magnetic fields, right? We learned that in our previous lecture. So because there's current in the wire, right-hand rule, you curl your fingers in the direction of the current flow. So current, of course, will flow through your coil like this. So the current, coil your fingers in the direction of the current flow, and your thumb points in the direction of the magnetic field that's created by the current. So in other words, you have a magnetic field that's created in the laminated core inside the coil like this. Right? The current that you applied, it's alternating. So that means that the magnitude of the current changes with time, right? This is a sinusoidal current that characterizes the AC or alternating current. The magnitude of the current changes with time. So in other words, the magnetic field that's generated here will also have a varying magnitude or amplitude relative to time, right? When the current is maximum, the magnetic field that it generates will also be maximum, right? When there's no current at this point here, when there's no current, then there's no magnetic field that's generated, okay? Right, now the magnetic field, we learned that magnetic field lines form closed loops, right? So the magnetic field will go around your laminated core in this manner. It will pass through the secondary coil. So through your secondary coil, you have a magnetic field that passes through. Okay, the magnitude of the magnetic field changes. So through your secondary coil, you have alternating increase and decrease in the magnetic field. And we learned yesterday in Faraday's law that if the magnetic field changes, that induces a current in the secondary coil. Right? Using the right-hand rule, you point your thumb in the direction of the magnetic field and your fingers curl in the direction of the current that's created. So in your secondary coil, you have current that is you have, come on, here. Is it not working? Yeah, you have current that is induced or created in your secondary coil because of the changing magnetic field in the secondary coil, right? Good. Does that make sense? How, it's like these two coils, they're not connected with each other, right? They're just coiled through this loop, but it's like magic. If you apply currents on this primary coil, currents appear in the secondary coil, right? And the current in the secondary coil is actually the current that is induced by the changing magnetic field that crosses or passes through that secondary coil. Okay, so it's all because of electromagnetic induction, right? So the primary coil, we can describe that by the number of turns or number of coils made on the primary, on this side of the core, right? So let's call that NP. It's the number of turns in the primary coil. In the secondary coil, again, you have this wire that's coiled around on this end of the core. We can characterize that coil by the number of turns. Let's say NS is the number of coils or turns in the secondary coil. Okay. If we put an AC or alternating voltage in the primary coil, that we call VP, that induces a voltage in the secondary coil because of electromagnetic induction. We call that VS. So we're just defining some variables here. NP is the number of turns in the primary coil, NS number of turns in the secondary coil, VP, that's the alternating voltage, right, that you apply in the primary coil. And as a result of the alternating voltage in the primary coil, that generates alternating currents in the primary coil, therefore creating alternating voltage in the secondary coil, VS. So we can relate all of this. The voltage that is created in the secondary coil, according to Faraday's law, is equal to the change in magnetic flux in the secondary coil times the number of turns in the secondary coil. So we can rearrange this equation, later. Yeah, but then the voltage in the primary coil is also related to the change in flux, magnetic flux through the primary coil. Okay, so we can rearrange these two equations to isolate dphi over dt because it's the same. It's the same magnetic fields, right? It's the same magnetic field that goes around this laminated core and goes through the primary and secondary coils, right? That means it's the same magnetic flux here. So rearranging these two equations to isolate the change in magnetic flux with respect to time, these two equations are equal. Hence, we have this equation, which is called the transformer equation, right? Vs over Ns is equal to Vp over Np. Yeah, we have that equation as a consequence of the flux being equal, change in flux being equal. Or we can rearrange this equation and collect onto one side all the voltage terms. So you have Vs over Vp. And on the other side, we have the number of turns, Ns over Np. Okay, so you have this relationship of voltages on the left-hand side and number of turns on the right-hand side. So this is the transformer equation that is maybe fundamental in describing how the transformer operates. Because if we look at this transformer equation, we can then classify two kinds of transformers depending on the number of turns in the secondary and primary coils, right? So here in this figure, this is the secondary, okay, secondary coil, and this is the primary coil, right? If you have more turns in the secondary coil compared to the primary coil, right, such that NS is greater than NP. According to this equation, if NS is greater than NP, then VS is greater than VP. What that means is that the voltage created in the secondary coil is greater than the voltage created in the primary coil. Okay. Right, hence this transformer increases the voltage going from primary to secondary. For example, the primary voltage is 110 volts. In the secondary coil, you have a voltage of 240 volts. Right? And because the voltage increased, we call this transformer the step-up transformer. Okay. Right? On the other hand, if the number of turns in the secondary coil, right, is less than the number of turns in the primary coil, as we can see in the second figure here, there are more turns in the primary coil compared to the secondary coil. If we look at the transformer equation, the consequence of that is that the voltage created in the secondary coil is less than the voltage created in the primary coil. Okay. That means that the transformer decreases the voltage. For example, if the voltage in the primary coil is 240 volts, right, at the secondary coil, the voltage is 110 volts. Right? Just an example, depending on the number of turns in the secondary and primary coil. And for this case, since the transformer decreased the voltage going from primary to secondary coil, we call this transformer a step-down transformer. All right. Okay, so step-up transformer, you want to increase, you use a step-up transformer if you want to increase the voltage. Say, for example, many devices that you buy in the United States, they have a mains voltage of 110 volts. If you bring that to New Zealand, okay, our mains voltage is 240 volts. Therefore, you will need, okay, to operate properly in New Zealand, you'll need to step up. You need to increase the voltage. Oh, sorry, your appliance operates at 110 volts. So that means that you have to step down the mains voltage that you get from New Zealand outlets down to the voltage that the appliance accepts, right? So in that case, you need a step down transformer. Or the other way around, if you have an appliance from New Zealand, this appliance operates at 240 volts. You bring it to the United States, the mains voltage is 110 volts. Okay? You want to plug your appliance into the voltage source, but 110 volts, it's not enough. You'll need to step up the voltage from 110 to 240 volts so that your device will work. Okay. Right. Does that make sense? Yeah. Okay, we'll look at an example later on. Okay, so this is an important equation, therefore, this transformer equation, because it relates the number of turns in the transformer to the voltage that you can generate in the secondary coil. So when this allows you to design a transformer by just looking at how much voltage you want in the secondary coil and then adjusting the number of turns in the primary and secondary coils in order to achieve the correct voltage that you want. Now, if you want an equation that relates the current to the number of turns, okay, we can use the definition for power. If we assume that the transformer is 100% efficient, I mean there's no losses, and that's perhaps the role of the lamination in the core, so we can to most extent assume that the transformer is 100% efficient. Energy conservation requires that the output power in the secondary coil should be equal to the input power in the primary coil. And power is defined as current times voltage. In other words, the current times the voltage in the primary coil should be equal to the current times the voltage in the secondary coil. Right? And if we use the transformer equation, we can of course, rearrange this equation to have this form: Vs over Vp is equal to, so we're moving Vp to the other side, so you have Ip over Is. Okay. Right, and then we substitute Vs over Vp is equal to Ns over Np. So we'll have Ip over Is is equal to Ns over Np. Okay. Or it's the same as flipping the equation: Is over Ip is equal to Np over Ns. Okay, so these two equations are equivalent. They're just flipped versions of each other. Right. So then we have an equation that relates the currents in the coils to the number of turns in the coils. Right. So again, if you want to design a transformer with a defined current in the secondary coil, knowing how much current you need to power your device, right? So you know how much current you need to have in the secondary coil. You can adjust the number of turns in your primary and secondary coils in order to achieve your desired current. Good. All right, so let's look at this example that sort of combines all the concepts and the transformer equations, right? You have here a high intensity desk lamp. It's rated at 35 watts. That means the power is 35 watts, but it requires only 12 volts, right? Voltage 12 volts. It contains a transformer that converts 240 volts household voltage, and we assume 100% efficiency for the transformer. Right, so in essence, you have here, right, if we draw how this looks like, okay, you have 240 volts mains voltage going into the transformer of the desk lamp, right? The desk lamp only needs 12 volts, right? So that means you have less number of turns in the secondary coil, right? This is the primary coil with NP turns. This is the secondary coil with NS turns. And your lamp only gets 12 volts. Right, so in essence, the mains voltage, that will be the primary voltage, because that's where you plug your lamp into the mains voltage, right? So the mains voltage will be the primary voltage. There's a transformer in your lamp. The transformer steps down the voltage from 240 volts to the required 12 volts. Okay, so 12 volts is therefore the secondary voltage in the transformer. Good. Does that make sense? The scenario. Yeah. So that's the scenario of the problem that we're dealing with. Right. So that sort of already answers the first question, right? Whether is the transformer step up or step down. Okay. Right. So I hope it's clear, right? So where is that? Oh, here. So yeah. So of course it's a step down transformer. Yep, you want to convert 240 volts mains voltage. You want to convert that to 12 volts. You want to decrease the voltage using the transformer. Therefore, it's a step down transformer that you need this case, right? And the second question, what's the current in the transformer's secondary coil, right? So what we know here is that the power of the lamp, okay? The lamp, of course, if you look at our drawing here, the lamp is in the secondary, will take the secondary voltage. So that means the power in the secondary coil is equal to the current in the secondary coil times the voltage in the secondary coil. Or yeah, we need the current. Current in the secondary coil is power over voltage. The power is 35 watts and the voltage is 12 volts, right? We're looking at the secondary coil because that's what the current that we want to solve. Okay, so in this particular example, we use the definition for the power in the secondary voltage because, of course, that's what we know. We know what the power is and we know what the voltage is. You can, of course, use the transformer equation relating the currents, right? IS over IP is equal to NP over NS, okay? You can also use this, but if you use this equation, you don't know the number of turns in the coils, and you also don't know the power in the primary. So that leads you to a dead end. Okay, but if you know the number of turns and you know the primary current, then of course you can use this equation. Right? So now we have determined the current in the secondary coil. The next question is, what's the resistance of the lamp when it's turned on? Okay. So the lamp that's in the secondary coil, right? We've determined, we know the current in the secondary coil is 2.9 amps from the previous question. The problem tells us, the statement of the problem gives us the voltage in the secondary coil is 12 volts, okay? Right, we know the current, we know the voltage. Ohm's law gives us the resistance, right? So resistance will be voltage in the secondary divided by the current in the secondary. Voltage is 12 volts divided by 2.9 gives 4.1 ohms. Good. Any questions about the example that we've looked at? Okay, so we've seen that, right, the transformer works because we have an alternating current coming from an alternating voltage source, right? And it's the changing in the current amplitude or current magnitude that actually induces the current in the secondary coil. So transformers only operate on AC, but a DC or a direct current voltage is also will not generate an induced current in the secondary coil, right? So an alternating current is one where the amplitude or the magnitude of currents is changing with time. A direct current, of course, is one where the current is constant throughout time, right? So if your current is constant throughout time, the magnitude is not changing, the magnetic field it generates will also have a constant magnitude all throughout. And that's why a direct current voltage or a DC voltage or current will not generate an induced current in the secondary coil. But direct current voltages or DC voltages are useful for automobile ignition. The reason behind that is, right, if this is your voltage, so y-axis here is voltage, okay, and x-axis is time, right? When you turn on the engine of your car, you're essentially, you have this sharp increase in the voltage in the car, right? And that sharp increase in the voltage is essentially a change in a sharp increase. Let me start over. Okay, when you turn on the engine of your car, the voltage increases sharply, like this. The sharp increase in the voltage creates a sharp increase in the current. You essentially have a current that changes amplitude in a similar manner as the change in the voltage here. As we said, if the magnitude of the current changes, that induces a current in the secondary coil, right? So in the secondary coil of your car's transformer, you create a induced voltage and an induced current, right? And that induced current or induced voltage then creates a spark that ignites the gas mixture in the car. So in other words, a direct current voltage or current can also make a transformer operate or make a transformer work, but only at certain times. It's only during the turn on or turn off process where the voltage changes drastically, where you have an induced voltage that's created in the secondary coil. In all other times, when the current magnitude reaches steady state and you have a constant current like so, then there is no induced voltage. And of course, there's no induced current in the secondary coil. Right? Okay, so any questions so far about, so what we've learned today is two applications of electromagnetic induction. Electromagnetic induction, of course, tells us that if you have a changing magnetic field, that induces a current, and that's how, firstly, an electric generator operates and how it's able to produce AC currents, and how a transformer operates inducing a current in the secondary coil if you have a changing current in the primary coil. Okay. So we have, in essence, we have come to almost the end of our journey here, because we started with magnetic fields creating currents. If you have, magnetic fields being created by currents, if you have changing currents, and if you have changing magnetic fields, that creates currents, and if you have currents, that creates magnetic fields. And it led us to understanding how alternating currents are generated. So in our next lecture, we will then focus on analyzing circuits with alternating currents. But before we go to circuits, I'd like to leave you with this rather interesting video about magnetic fields and its applications. Well, maybe not so practical applications, but fun applications. So I think I have to transfer to the PC here. Okay. Will you try that?